Hey everyone, today we're going to look at some word problems for rational functions. So we are going to formulate, meaning we're going to read through the word problem, use some sort of formula to create an equation, and then we're going to solve that equation. So the first type of problem we're going to look at is motion. So motion problems involve distance, rate, and time. And we're going to set up a proportion, distance over rate equals distance over rate. So we're going to have two objects that we are looking at the distance and the rate of. Okay, so this first example says train A can travel at a constant rate from New York to Washington, a distance of 225 miles. So train A travels 225 miles. Train B, traveling 50 miles per hour faster, can get from New York to Richmond, which is a distance of 375 miles. So 375 for train B. Find the speed of each train. So these two trains are traveling that distance, 225 miles and 375 miles, in the same amount of time. So we know that train A has a rate and train B is 50 miles per hour faster. So I'm going to say that train A's rate is X and train B's rate is X plus 50. So whatever train A's was, plus 50 miles per hour. So you can see the left side of our proportion is going to be distance over rate, so 225 over X. And then the right side of our proportion is going to be distance and rate for object B. So distance was 375, rate was X plus 50. So anytime we have a proportion where it's just a fraction equals a fraction, we're going to cross multiply. So here I have 375x equals, here we're going to have to do 225 times x, which is 225, and then 225 times 50, which is 11,250. So, sorry, that should have an x, plus 11,250. So we're going to solve for x. I'm going to subtract the 225x to the left. So we get 150x equals 11,250. And then I'm going to divide by 150 on both sides. When I do that, 11,250 divided by 150, I get a rate of 75 for train A. So X equals 75, and this is our rate, miles per hour. Okay, so it's really important that we can decipher what X stands for. So up here, my X is 75. So I know that the rate of train A is 75. This train B is 75 plus 50. So rate of train B is 125. So we can say train A is 75 miles per hour. Train B is 125 miles per hour. Okay, second type of problem is going to be work problem. So this is when you are working together with someone else to finish a job. So this says that it's going to relate two or more workers that work at different rates and see how long it's going to take them to finish a job when they combine their efforts. So you can't just say that they're going to split it evenly, because if one of them is working faster, if they continue working after they finish half the project, they're going to be able to finish it in less time. So we're going to have 1 over the time for one person to finish it alone, plus 1 over the time for a second person to finish alone, and that's going to equal 1 over the time for them to work together. So of course, if we had more than 2 people, we would just add additional fractions on the left side of this equation. So Jack and Jill are building computers. Jack, when working alone, can build a computer in 20 hours. When Jack and Jill work together, they can build a computer in 7.5 hours. How long would it take for Jill to build a computer alone? So this can be, right here, this can be Jack because these fractions over here are for alone. So that can be Jack, this one can be Jill, and this last one can be what amount of time it takes them to work together. Okay, so we know that when working alone, Jack can build a computer in 20 hours. So Jack alone time is 20. So that's going to go down here in the denominator. Okay, we know also that when working together, it's going to take them 7.5 hours. So working together over here is 7.5. What we don't know is Jill's time alone. That's what we're trying to find. So I have 1 over 20 plus 1 over x equals 1 over 7.5. And we know from our previous lesson that in order to add fractions, we have to get a common denominator. So I see that this first one has a denominator of 20. It's missing an x and a 7.5. Okay, this next one has an x. It's missing a 20 and a 7.5. And this last one has 7.5. We're missing a 20 and an x. So now all three denominators, because remember, when we multiply on the top, we multiply on the bottom, even if I'm not explicitly writing it. So all of our denominators now have a 20, an x, and a 7.5. And it doesn't matter the order that we multiply or we write those, because we're not actually going to multiply them out. Because now that we have a common denominator, we're just going to be working with the numerators. Okay, so over here on my first fraction, I have a numerator of 7.5x. On the second one, I have a numerator of 150. And on the last one, I have a numerator of 20x. So I've got this equation, 7.5x plus 150 equals 20x. I'm going to subtract the 7.5x from both sides. So I get 150 equals, 12.5x. And then I'm going to go ahead and divide. So 150 divided by 12.5. And we can see that equals 12. So x equals 12. We can come back up here and we see that this x value that we were solving for is the time for one person to do it alone, and that was Jill's fraction. So for Jill alone, it's going to take her 12 hours. So just like when we had people working together to do something faster, we can have things working against each other that actually make things take longer. Okay, so when we are working against one another, we have a similar formula, except we are going to be subtracting our two fractions instead of adding them. So we take the time for something to happen, and then we subtract the force that's working against it, and that's going to give us our time working together or against, as it were. Okay, so an oil tank has two inlet pipes and one outlet pipe. One inlet pipe can fill the tank in 12 hours. The other inlet pipe can fill the tank in 20 hours. The outlet pipe can empty the tank in 10 hours. How long would it take to fill the tank with all three pipes open? So basically, we've got this tank that we're trying to fill up with oil. Okay, there's two pipes that are putting oil in. So two can get it done faster. But then we've got this pipe at the bottom that's letting oil out at the same time. So as it's coming in, some is leaving at the bottom, but the two that are filling it up are filling it up faster than that one that's leaving. So eventually it's going to be full, but we don't know how long that's going to take. That's what we're going to try to figure out. So you can see up here in our first equation, we want the time for filling first, which two pipes are working together to fill it up. So we're going to use addition with those two. And then we're going to subtract this pipe at the bottom. because if we're working together, we add. If we're working against, we subtract. So right here is going to be the time for filling. So it says that one can do it in 12 hours, the other can do it in 20 hours. So that's working together. And then this other pipe at the bottom is working against. And if it was full and nothing was coming in, this pipe could empty it out in 10 hours. Okay, we're looking for the combined efforts of the filling and the emptying. How long is it going to take this tank to fill? Okay, so looking at our denominators, let's see what's missing. So I have a 12, a 20, a 10, and then X. So this first fraction, and you could find your least common denominator and do a little less multiplying. I'm just going to go ahead and if it's missing something, I'm going to put it on there. So I'm missing a 20, a 10, and an X. This next one, I'm missing a 12, a 10, and an X. Next one, I'm missing 12, 20, and X. And then this right side, I'm missing 12, 20, and 10. So if I multiply these out, I end up getting 200X plus 120X minus 240X equals 2,400. So I'm going to combine things together. Over here on the left, I get 80X. On the right, I get 2,400. And then when I divide by 80, I find out that X equals 30. So over here, X was the time for all of these working together. So as we're filling and emptying, it's going to take 30 hours to get it completely full. Even though working together, the 12-hour and the 20-hour pipe could have probably filled it in about 8 hours, because we've got that force working against us and emptying it at the same time, it's going to take us 30 hours to fill that tank completely up. Okay, the next scenario we're going to look at is also working for and against some sort of force. This has to do with either wind or water. So if you think about swimming in a river, if you're swimming downstream, the current kind of carries you and makes you swim faster. If you're trying to swim upstream against the current, you're not going to make it very far, very fast, because that current is kind of pushing you back at the same time. So in this first example, it says Garth can row 5 miles per hour in still water. So that means that that's his speed if he doesn't have anything helping him or harming him. So like, for instance, in a lake or a swimming pool where he's just swimming on his own and there's no water going for or against him. So in still water, his standard speed is 5 miles. Okay, it takes him as long to row 4 miles upstream as 16 miles downstream. How fast is the current? So for our rate here, X is going to be his speed in still water, okay? And then C is going to be the current. So if he's going against the current, we're going to subtract the current speed because it's going to harm him. It's going to slow him down. If he's swimming with the current, we're going to add the current value because it's helping him. It's carrying him faster. So when we're going upstream, it says that he's going to only row 4 miles, and his rate is going to be the speed 5 minus the current. Okay, because we don't know what that current speed is. That's what we're trying to figure out. But we know that his still speed is 5, and then the current is pushing him back at a certain rate. Okay, we don't know the amount of time. So then downstream, when he's going with the current, he can swim 16 miles, and it's going to take him that same amount of time. And his rate is 5 plus C, because that current is going to help him out. Okay, we know the time is the same, but we don't know what it is. So our proportion is going to be set up the same as it was for our train up here, because we're still working with distance, rate, and time. So we want distance over rate equals distance over rate. So distance, rate, distance, rate. So looking at my table, upstream, I can swim 4 miles at a rate of 5 minus C. Downstream, I can swim 16 miles at a rate of 5 plus C. So we're going to go ahead and cross multiply because we have a proportion. So if I do this one, I have 20 plus 4C. On this one, I have 80 minus 16C. So I'm going to go ahead and subtract the 20 to the left or to the right. I'm going to add the 16C to the left. So I get 20C equals 60. And when I divide, I find out that C equals 3. Okay, and we're measuring the speed of the current, so that's going to be miles per hour. Okay, I could then find out the amount of time that he is taking to go those distances if I wanted to. The question just asked me how fast the current is. But now that I know my rate is a 3 for the current, I could plug it into either one. So let's just plug it into the upstream. So my rate upstream is 2 miles per hour. So I could plug distance and rate in. So I have 4 equals 2 times T. When I divide by 2, I find out that T equals 2. We're measuring time in this for hours. So it's going to take him 2 hours to swim 4 miles upstream, and it's going to take him 2 hours to swim 16 miles downstream, or I guess row 16 miles downstream. Okay, the last scenario we're going to look at is inverse variation. So this tells me that I have a formula, y equals k over x, where k is the constant of variation. Okay, constant of variation means that it's going to vary at the same rate throughout the entire problem. It's not exponential, it's like a linear variation. So example 1 says, given that y varies inversely with x, and y equals 8 when x equals 3, what is the value of y when x equals 12? So here we have a y on the left side. So y is 8, and then x is in the denominator when x is 3. So I have 8 equals k over 3. Well, I'm going to solve that by multiplying both sides by 3, and I get 24 equals k. So my constant of variation is 24, but that's not what it's asking. It's asking what is the value of y when x equals 12. So we're going to have to write a second equation using our k value, because k is constant throughout the whole entire situation. And so we have, once again, y equals k over x. I want to look for the value of y. I know my constant is 24 now, and I want to know the y value when x is 12. So I would do 24 divided by 12 and find out that when x is 12, y is 2. So this right here would answer the question that was asked. But I first had to figure out what my constant was before I could find that y value. So we just had 2 little simple equations that we solved. Okay, so applying that to a real world situation. The number of flowers F that a gardener can plant along the border of a garden varies inversely with the distance between the flowers. So what that means is as the flowers get closer together, so as the distance gets smaller, the number of flowers he plants gets larger because he can fit more in the garden that way. So inverse variation means as one value gets smaller, the other gets larger. So if we increased the space between flowers, the number of flowers would decrease. Okay, if a gardener can fill the border with 30 flowers planted 12 inches apart. How far apart should the gardener plant 36 flowers? So it's not really going to matter which one we call X and which one we call Y, as long as that stays constant throughout. So I'm going to say that X is the distance and Y is the number of flowers. Okay, so we have Y equals K over X. So number of flowers, 30, equals K over X, which is distance, 12. So in order to solve for K, I'm going to multiply both sides by 12. And we find out that K equals 360. Okay, that doesn't have a unit. It's just our constant of variation. So then we can use that. We want to know how far apart should the gardener plant 36 flowers. So that's going to be our Y value. So we can say Y equals 36 equals K, which is 360 over X. So we're going to need to solve for X. So we get 36X equals 360. We're going to divide that by 36. We find out that X equals 10, and this is distance, which we're measuring in inches. So he would need to plant them 10 inches apart to fit 36 flowers, which makes sense because we're putting more flowers than originally, and our space is less.